So as mentioned, I'm William Ryan. I'm going to be presenting today on some work which I did with Ellen Avers and Don Moore at the Haas School of Business. Don Moore, apart from being here on the slide, is also right over there. So he's partially to credit for this work. So what I'm going to be talking about is most specifically Poisson regressions, a particular type of regression used often in psychology, and why there's some issues with it which might not be immediately obvious. And if you're not someone who ever encounters these, you're not someone who's ever read a paper using Poisson regressions, I think the way that this presentation will mostly be interesting to you is as sort of a case study or example of how to take a regression technique and evaluate how effective it is, evaluate how bad violations of its assumptions are. So, Poisson regressions have some issues. And to demonstrate this, to make this intuition really clear, what we're going to do is we're going to run an excellent, extremely well-designed study of an extremely false hypothesis. So we're going to use open data, we're going to use open materials, we're going to pre-register every single one of our analyses, our DVs, our IVs, everything's going to be in there. So we're using really what is kind of best practices in science. But we're going to be testing a completely ridiculous assumption. So we're going to be asking, does priming people with thoughts of the ocean elicit hunger for fish or sympathy for them? So let's talk about how we operationalize this. So in classic traditions of psychology, we have 99 undergraduates as our sample. And we've got two conditions shown by our dog models here. So we have a control condition where the experimenter is wearing a black shirt, and we have an experimental condition, an ocean priming condition, if you will, where the experimenter is wearing a blue shirt. So then what we have people do is we have them complete an unrelated survey, and then our dependent variable, our outcome variable, is how many Swedish fish they ask for as a reward once they've completed the survey. So our expectation is that there's going to be a difference between people who are seeing the blue shirt versus the black shirt in the number of Swedish fish they take. Maybe they'll take fewer because they feel like they shouldn't be eating fish anymore. Maybe they'll take more because now they're hungry. So here's our results. So we find when we look at the count of Swedish fish taken, there actually is a significant increase in the number of Swedish fish eaten when the experimenter is wearing a blue shirt versus a black shirt. But we pre-registered this. And one of the things we pre-registered was we're going to measure Swedish fish in a couple different ways. So maybe we want to make it really comparable to other foods. So let's use grams. So there's 5 grams per Swedish fish. So let's just multiply everything by 5 and see what happens to our test. So now it's even more significant. I'm actually not sure how many asterisks to put here, so I just put a lot. And then finally, let's look at the calories per Swedish fish. So let's just take our original result and multiply it by 8 calories per fish. And now you can see ocean priming is actually the most significant result, potentially, in the history of psychology. And we have every asterisk there. So we thought of a cool pun title for our journal article. Got ready to publish in a top journal, and released this huge flood of listicles about a weird wardrobe trick to help you lose weight. So the only problem here is that this finding is obviously false. So the next question is, how did this happen? So the basic culprit, as you might guess from the name of the talk, is our use of Poisson regressions. So a Poisson regression is a type of regression commonly used to analyze count data. The reason people use it is because it consists of integers and it's censored below 0, just like count data is. However, it wasn't actually intended or designed to be used on a lot of the count data on which it is used. So it's supposed to be used to identify the number of events occurring within set intervals of time, not things like the number of pins stuck in a voodoo doll or a number of other sort of psychology DVs for experiments. And I'm going to use number of pins stuck in a voodoo doll as an example for a second, but I should note that it's actually a surprisingly well-validated outcome measure. So props to pins in a voodoo doll. So to see why it's a problem when you're using Poisson regressions for these distributions which it's not intended for, let's give an example. So let's say we have this distribution of data which meets this basic assumption of Poisson that the mean is equal to the variance. So let's say this is number of pins stuck in a voodoo doll of your partner after they eat your raspberry yogurt out of the fridge. So you can see mean equals variance. When we fit a Poisson distribution to it, it fits pretty nicely. However, let's look at another distribution of data where this assumption is violated. So here's the distribution of pins stuck in a voodoo doll after they eat your blueberry yogurt. And you can see this is an extremely similar distribution, except it has an increased variance due to these sort of outliers on the edge here. So now when you try to fit a Poisson distribution to that, you end up with a distribution which really doesn't fit the data well, and which makes there appear to be a difference between these two data sets, even when one does not actually exist. So that's sort of the engine which is driving false positives when you're using Poisson. So the next question you might have is this actually a problem? Is count data actually not have a mean equal to variance? So what we're showing you here is just a quick convenient sample of articles using Poisson on count data in top psychology journals, which also reported their means and standard deviations. And you can see that if we're just showing on this log axis here, the ratio of variance to mean, a lot of these studies are in fact above the mean to variance ratio being equal, except for this one study here, which was perfectly appropriate to use Poisson. All the ones up here, variance is over mean, probably going to have some issues. So let's talk about how bad violations of these assumptions are. So there's a lot of cases in statistics where it's actually not that bad to violate some of the assumptions of a regression model. And it's possible Poisson could be one of these cases. It turns out it's not. It's actually very, very bad to violate these assumptions. So the way we did this was we basically did some non-parametric simulations. So we generated a bunch of data sets, randomly assigned half the data set to a control condition, half the data set to an experimental condition, and ran a Poisson regression to see if there's a significant difference between those conditions. And that's just a graphic of my computer over the last few months as it's been struggling to run these simulations. So once we've done that, we could actually simulate for a variety of variance to mean ratios, how often do you generally get a false positive result? So just to orient you to this graph, on this y-axis, we've got the percentage of significant p-values. So if all is well, you'd expect that to kind of stay at 5%. And then on the x-axis, we have the variance to mean ratio. So it's going to increase from 1 to 1, where everything's fine, all the way up to 15 to 1, where you have a significantly higher variance to mean. So when we do these simulations, as you expect, when the variance to mean ratios are equal, when it's 1 to 1, you get just 5% false positives. However, as we increase the variance to mean ratio, you quickly see far more false positives occurring. So even when you've gone to just a 2 to 1 variance to mean ratio, you're already tripling the number of false positives, and it only gets worse from there until eventually, once you've gotten to this 15 to 1 variance to mean ratio, you're actually at above 50% false positives with each of your statistical tests. So Poisson is actually extremely sensitive to violations of this assumption, and it's very easy to get false positive results when you use it inappropriately. So this can help put our results from our fish priming experiment into context. So remember, we had 3 different DVs we measured per our pre-registration, right? We had the number of fish taken, the grams of fish taken, the calories of fish taken, and all we did to get from one to another was multiply by a scalar. So in practice, the candies had a 3 to 1 variance to mean ratio. That was sitting at about the 20% false positive rate. However, when you switch to grams, you're already at a 16 to 1 false positive ratio, so it was more likely we'd find a significant effect on grams than not. And to actually show you where calories fall, I'm going to have to break this axis and go all the way out to 25 to 1. So it's incredibly likely when you have that variance to mean ratio that you're going to get a false positive. And we can also take that scatter plot of studies showing count data, and we can compare it to this false positive rate to give an idea of how much of an issue this might be, not just for our innovative ocean priming study, but also actual studies already in the psychology literature. So first of all, there's this 50% of studies which are above a 1 to 1 variance to mean ratio. So 50% of them have at least a doubled false positive rate based on these simulations. So they're at least 2 times as likely to be false positives as they ought be. And if you break it down more finely grained, that 50%, you actually see 20% are between 1 to 1 to 5 to 1, 15% between 5 to 1 and 10 to 1, and then 15% are actually above a 10 to 1 variance to mean ratio. So about 15% of all the studies we reviewed are more likely to get a false positive than not. So this really is a big problem within the existing psych literature where they're using Poisson. And there are really good alternatives to Poisson for count data. So some of you might be familiar with some of these. There are things like negative binomial regression, where you allow the variance to mean ratios to differ, simple non-parametric permutation tests, or even just a totally basic linear regression or t-test, just OLS, as well as a bunch of others. So the next thing we'd like to do is we'd like to compare those alternatives to Poisson regression, see if they give the same pattern of false positives. And here we're just using the most standard basic version of these tests implemented in R. So if you look at negative binomial, it stays robust all the way out to a much higher variance to mean ratio before it starts to fail. And if you look at permutation tests or OLS regressions, they never increase the false positive ratios relative to Poisson. So these alternatives which exist are going to be much, much less likely to give you this errant false positive than a Poisson regression is. However, I guess a lot of you are economists, so trade-offs, big thing. Maybe there's a trade-off where Poisson regression gives, yeah, more false positives, but it also gives fewer false negatives. So you're making this trade-off where you're saying, okay, well maybe it's a lot better to just not miss these, not have a mistaken null result than to not have a mistaken positive result. I think not many people would agree with that, but it might be a trade-off which exists. So to do that, we also compared for a bunch of different Cohen's d's, when the assumptions of Poisson are met, what is the false positive rate you get for all these different methods? And it turns out it's not any higher. So if we look at this graph, I promise you there are 4 lines on this graph, not just 2. The false negative rates are almost identical across all of these different methods, no matter which one you're using, as long as the assumptions of Poisson are met. Okay, so of course, if the assumptions of Poisson weren't met, let's say there's a huge variance to mean ratio, then yeah, Poisson is going to have more false negative, or have fewer false negatives, but it's just going to be as a virtue of having more false positives, right? In the same way that if I invented the Ryan test of statistical significance, which is just like, yes, that is significant, that would have 0 false negatives, but it would be at the cost of 100% false positives, and probably no one would use it, hopefully. So, what's the big issue with these false positive p-values? So we think there's a couple problems. So unlike many other ways, like p-hacking of getting these false positive results, these false positives actually have extremely low p-values. So when you're going through and doing something like a p-curve or many other estimates of publication bias, it's going to give a distorted sense of what the distribution of p-values actually is, and it's not going to be able to account for these sort of kind of methodological errors. It's also going to harm meta-analyses. It's going to be bringing in all these incorrect effect sizes. And even if you are dealing with a true positive result, it's going to give you a really incorrect idea of the actual sample size that you should be having if you're just basing it on past published research or on past estimates in your own work. So what is the message sort of in relation to Poisson regressions here? So if you're writing a paper analyzing count data, use something else. A t-test is often fine if all you're concerned about is false positives, false negatives, and the other alternatives to Poisson are extremely easy to implement. Plenty of examples in the data and code which we've posted. It's literally just an extra argument to your regression. If you're reviewing a paper with Poisson, almost always you should ask for something else. It's very, very rarely appropriate. Usually something else is going to give a better estimate. So I'd like to thank my collaborators. So quickly, Ellen Avers and Don Moore, who I'd mentioned already. Also assisting with data collection were Stephen Baum, Katerina Goncharova, and the Bureau of Research Computing here at Berkeley, who helped my laptop not completely melt while running this project. And we got really great revisions and feedback from Stephen Antonopoulos, Kristen Donnelly, Yoel Mbar, Alex Park, and Sydney Scott. So thank you very much to them.
When you're estimating in the literature how often these occur, you're restricted only to those that report both the mean and the variance. Is that right?
That's correct.
So are you worried that that's a bias set, that it's all the ones that are not reporting the variance, that maybe they're all fine, they all have a 1-to-1 ratio?
I think my expectation, my expectation would be there is some selection bias there, but it's probably in the opposite direction. I think if someone's not posting their means and variance, it's more likely that the means and variances look bad, just given the incentives which exist. But I do think that's a good question. So it's possible the results are skewed the other way. I think if anything, though, it's probably even worse than it looks. Yes.
I'm sorry if I missed this, but did you, given your sample, get an estimate of what proportion of papers were using Poisson in some set of psychology journals? Yeah.
Yeah, definitely. So that's actually what we're working on right now. So we have some wonderful RAs from Don's lab who are going through and they're coding for a bunch of psych journals, not only sort of every paper which uses Poisson and surveying those authors to see sort of what drove that. They're also looking at sort of what is the kind of denominator, like what is the amount of count data overall. So I think that's a really good question. I think we have found sort of a suggestive time trend that at the very least the rate is increasing, not decreasing, but it's really hard to say before we do that kind of comprehensive search. Yeah.
I just think it's weird that psychologists use Poisson because even back when I was in grad school in the 90s, when Stata became popular, we were taught that you type in NB-reg, not POIS, and then you hit enter because I mean, it just, I don't know, it just seems like in political science, everybody knows this. So it's kind of weird. That's just a comment.
Yeah, no, it's a little bit bizarre. Right, it does seem like it is present in a lot of stats textbooks. So I think part of what might be driving it is like if you just have an overall graduate stats course, they deal with count data only briefly, it's easy for the lecturer to say sort of like Poisson's pretty good, maybe look at alternatives, and maybe it's just kind of a lack of knowledge thing. But yeah, it is surprising to us as well. And that's part of what hopefully the survey will answer, like why is this use still happening?
Thank you.